Use the fact that the limit as theta goes to 0 of the sine of theta over theta is equal to 1 to find the limit as t goes to 0 of the sine of kt over t, where k is some constant. First, let's take a look at the graph of the sine of theta over theta. Using the Desmos graphing calculator, we can see that the graph of the sine of x over x approaches a y value of 1 as x approaches 0 from the left and from the right. Let's change the coefficient to, let's say, 2. Now we can see that the graph of sine of 2x divided by x approaches a function value of 2 as x approaches 0 from the left and the right. Let's change this to a 3. Now the function is approaching a value of 3. Let's change that to a half. And we can see that the function is approaching a value of a half. So we have a suspicion that this limit is going to be equal to whatever coefficient we have on x in the numerator. So now looking at this limit, we see that the coefficient on t is k. So we have a suspicion that this limit is going to be equal to k. Let's see if we can show it. If we were to multiply the top and the bottom of this by k, which we can do because k represents some constant, so we're really just multiplying by 1, we could rewrite this as the limit as t goes to 0 of k times the sine of kt divided by kt. Now this k in the numerator out in front of the sine function is just some constant that we can pass out in front of the limit. So we have k times the limit as t goes to 0 of the sine of kt divided by kt. But now let's do this. Let's let theta equal kt. Then we can rewrite this whole thing as k times the limit as t goes to 0 of the sine of theta over theta. But something else that we might note is that when t goes to 0, this would imply that kt would also go to 0, which would imply that theta is going to 0. So we can rewrite this limit as k times the limit as theta goes to 0 of the sine of theta over theta. But we know that this limit is equal to 1. So this just becomes k times 1 or k.